Hi everyone, could you see my screen? Okay, so let's start. So today, from today onwards, I will uh, introduce how we deal chaos in a sense of little bit in a mathematical sense. So first of all, I want to say what do you means uh, when you see the word chaos, what the first thing pop up in your mind? If you can tell me, then I can understand what do you think about chaos. So, huh. Hmm. Yeah, it is true. That's the thing, that first thing pop up in your mind. But for the meaning of the chaos, I want to say that the chaos word chaos first came from this Greek letter that is this chi alpha o sigma. So these basically by these they mean that the the nothingness the nothingness that was there before the creation, that was meaning by this word chaos. But later on Roman changed the by using that word, Roman changed its meanings. They mean it that the rootless mass or shapeless mass from which the order and harmony came in the society. And then later on, as you suggested, that we use the word meaning of the word as synonym as chaos, as synonym as irregular disorder and irregularity, right? Disorder and irregularity. Now you see, from when is the first time when people see that these things uh, we can see from a simple equation. So first of all, I want to say that in the beginning, when the Newton was there, what he done, that uh, uh, he he just mathematically shows us that the governing law which we are seeing in this art is not different from the heavenly body, the celestial body. In the previous time, in the Newtonian era, they all think that the in the sky, in the heaven, the sun, earth, and sun follows some other laws. Was what Newton interestingly saw mathematically, that they follows the same law, and all the thing was very successful, and all the thing was predictable and irregular thing. Now this is all for the two body problem when only earth and sun is there, or the earth and moon is there. For these two body problem, suppose this is sun and this is earth, if you solve the Newtonian gravity, you will see that you will find out some irregular motion. Now the first problem arrived was when we want to solve the sun, earth and moon together three body problem. Then the problem arises. So problem was basically that we can't solve this the sun, earth and moon problem by simple Newtonian gravity equation. So there is a mathematician named Poincaré in 18 something 1860. So what he want to see, whether these three system we can't solve exactly from the Newtonian equation, but he asks whether these three system are stable or not. Stable means are they will follow, means they will be in close contact of each other for larger period of time. To do so, since the Newtonian equation is very hard to solve for three body problem, what he did, he discovered a topological method. So don't worry, we will not go deep into those things, but for the history I told by means what he did, he observed the system for after some period, suppose time t. So after time t, suppose these three will the coordinate of these s, earth and moon will be something, suppose x1, x2, x3. Now after again 2t, it will be x, suppose x, this is time t equal to 1 to x1, x2. Okay, let me write it in this fashion, then it will be clearer. So this will be, suppose sun, this is earth, this is moon. So this is sun, this is earth, this is moon. So you see the continuous equation becomes maps. So this is technical term, but what basically he did, that he make easier the problem by introducing this mapping, and by doing that what he found, that this system become, from the very simple equation, this system become very chaotic, very irregular, but he can't prove that whether these things are stable or not. So these become an open problem to us, that from whether from the Newtonian equation we can prove that the stability of the three body problem, and it becomes a very problem for the mathematicians who have a prior knowledge of very much mathematics. So then it was thought that yeah, indeed it could happen that from the predictable dynamics the chaos can come, but later on in the 1960 there is another guy whose name is Lorentz. During he actually studied the weather. So during their study of weather, he found that if from three very simple nonlinear equation, it is not the as much as complicated as three body problem what was dealt by this Poincaré, but from this simple three equation, what he found that chaos can occur simultaneously. Then means obviously he can't do by hand. It is when the computer was invented, and with the help of computer, what he found that although that the motion, although that the trajectory of that that the simple weather forecast problem is very chaotic, but what he could from the computer from the use of computer, what he used, that there is a attractor which is Lorentz attractor, that it is very chaotic, it can go here and there, but what is the thing is that it can't move very further, it can't go anywhere, it will remain constant in certain region of the phase space. Now from then it now after discovery that thing, everyone was not interested in chaos, until there is a famous book published in 1980s which is called Chaos by James Gleick, and after then the chaos become very popular, and in the 90s the in the television show also the chaos came. So from then the chaos become very popular. Now, but to know the chaos in a very simple way, there is no way to know chaos in very simple way. You have to know prior knowledge of non-linear, very much mathematical background. Now here comes another guy in I think in 90s. It's I think in 1970, I think 1978 or something, a guy called Robert May, who was a population biologist. He found that 1976, that Robert May in 1976, what he found that the chaos can come from a simple, very simple equation, from simple equation of the population dynamics. Suppose you think that there is a populations of insects, and as these as he is a population biologist, so what he studied, that what is the number of individuals after every year. Now when he documented that observation, what interestingly found that the in the next, from since these insects only reproduce single in a year, means they only give birth child only one in a year, so it looks very simple that if I know how much individual was there, suppose n individuals was there at time t, what will be the number of individual nt plus 1 at the next year. But what he found that these equation will be like that, nt equal to nt into 1 minus nt by k. So don't worry, I will construct this equation. So from this simple equation, he couldn't predict the what will be the next year, what is the size of the population at the next year. Now from there, it opens a window for a who has a small background, who can use computer or at least calculator. He can do by own self, that he can see how chaos can came, how we can see the chaos in the very simple mathematics. Now from then, this is called map, because this is called difference equation, or it is called map. Now from this equation, we will see how the chaos will came into the picture. Now in the what is the problem in the differential equation that was studied by the Poincaré and the Lorentz, that was the differential equation. So in the differential equation, you need at least three or more, or at least 3 degrees of freedom. Means you to see chaos in the differential equation, you need at least 3 coordinate, then you will see that chaos. But in map, in the context of map, you can see or you can observe the chaos in only 1D in the difference equation. So for the map, I will use difference equation, and in the only one dimensional we can study the chaos. Now this is very interesting, because you see, every time we want to seek for simplicity, but what chaos teaches, that means why we seek simplicity, because we need predictability in long run. But what chaos teaches, that if we achieve the most simple thing, but we couldn't guarantee that chaos will not appear, and if the chaos appear, the predictability will be lost, and it will become irregular and very disordered thing. So that is very contradictory things. That's why I am interested in the chaos, because it teaches us something in our life, that whatever we do for the simplicity, but we can guarantee our future, or we can guarantee our order in our future. So that's the thing. Now that's the basically how the chaos came into the picture, and we will basically in this course we will only study the difference equation or the map. We will not touch the differential equation because it needs a very rigorous mathematical background. That's all. And if you have any question, you can ask me. Okay. So if you don't have any questions, so I continue. So today I just want to give you a basic introduction of the chaos, basic introduction of the chaos. So that's all. And the chaos is another thing is very important for the chaos, because of that thing, that whether Means as there is a, if you know that Laplace once told that if we can collect all the initial condition, then if we put all the initial condition in gigantic computer, we can predict everything what will happen tomorrow, and what will happen in the future, we can predict all those things. But there is a catch what he missed, and that give rise of the chaos. And the definition of the chaos is basically based on these things. I will go deep into these things. So first thing is, definition is the sensitive dependence on initial condition. So you can see there is a subtle thing, that is that what Laplace says, that if you give me all the initial conditions, I can tell you the future. But you see, if the system has a sensitive dependence of the initial condition, that tells you that if you cannot give the exact initial condition, if suppose if you give something differ from the very small differ from that what is actual initial condition, then you see the system in the long run the system will follow another future. So that is basically sensitive dependence on the initial condition. If you choose two initial condition very close, in the long run they will far apart from each other, and you can't predict from this future. You can't, there is no correlation between this future and this future. Now so I want to say one simple thing, that things very interesting thing, why we can't give all the initial conditions. So if you think that initial condition means, if you know that there are more irrational number than rational number means that number which we can write in this form, that p by q form. If suppose there is a number, suppose 0.25, suppose there is a number 0.25, it is a rational number because we can write in this form. Now there is a number that is pi, we can't write it in the form of any p by q form. Obviously you will say that we can write it is 22/7, but you see this is a approximate of the pi, it is not the exact value of the pi. So pi is basically a irrational number, you can't write in this fashion. So if you think there is a lot more irrational number, this is a mathematical way, there is a proof that the number of irrational number is much more higher than the rational number, even that the irrational number is the size of the irrational number, or the number of irrational number has between 0 to 1 is larger than the number of rational number. And in the mathematical way, it says that it's means comparative to irrational number, the rational number contains very small zero set. Now since irrational number can go infinitely, because its digits you cannot put an end to that irrational number, because and it goes infinite. So you see, since there is an infinite number, so if you choose arbitrarily any number from this 0 to 1, suppose 0 to 1, the probability of choosing an irrational number is near to 1. It is means not exactly 1, but it is very near to 1. So whenever you choose a number, suppose if you choose a number, suppose initial conditions, how you will give the initial condition? Initial condition means a number. So number means if you choose between 0 to 1, so you will probably get a irrational number. The probability is very high. Now since we can't, since pi, how much we can go to pi? Means some 3 digit, 4 digits, and if you go further, you will go with, so that 3 digit is different from the pi. So 22/7 is itself differ from the pi. Now if we, instead of pi, if we give 22/7, the initial condition will not stay here, it will stay there, it will come here. Suppose this is pi and this is 22/7. Now you see these two initial conditions differ by very small amount, but if the system has the sensitive dependence of initial condition, it will far apart in the future. So the predictability will be lost. So as Laplace says that if we have all the initial condition in our hand, we can predict the future. These have a catch that we can't give all the initial conditions, since the number of irrational numbers. So getting a irrational probability of getting a irrational number is near to 1. And the other thing is the transitivity. So I will go deeper into this concept. So for the sake of introduction, I will just say these things. So transitivity means, in the lucid way, transitivity means if suppose your system, if you define your system in such a way that it will take only value between 0 to 1. Suppose it will only take between 0 to 1, and transitivity means if you take any initial condition and if you see its future, in future transitivity says it will almost cover every regions of the 0 1. Means it says that it will, means while its future, at any time it will go to every regions of this interval 0 to 1. So if you it means if you observe here, if you want to observe only here, after some point you don't know when, but you can ensure that if the system is chaotic, after some time it will come in this region. So this is transitivity. And third thing is very interesting, that is called dense periodic orbit. So as we know, in the definition of the chaos, you see where the periodic orbit comes. Now when I say the periodic orbits, everyone will think that the period means most regular thing. So how can we include to define the most irregular disorder thing by the dense periodic orbit? So indeed, we need dense periodic orbit, but here we are not saying that these periodic orbits are stable. So there could be a infinite number of periodic orbits, but they are not stable. So every time the system comes to that periodic orbit, it will repel by that periodic orbit, and for every periodic orbit, if repelled by that periodic orbit, so it will roam around the space infinite. So that's why this dense periodic orbit is very essential, and you will see that this condition, that sensitive dependence of initial condition, is very crucial for the definition of the chaos. And later on we will see that as it is it is the signature of the chaos, but we will see that this is not a very strong condition for the chaos. So that's all. And now this is the things. Now what we will see, because you can take a equation and you can show that mathematically, means in computer, if in computer, if you put that dynamics, you will see that chaos appears, but in what mathematical sense you can tell a priori without a computer that the chaos is present there? That is our goal. So how we can tell that, how we can prove the presence of chaos mathematically? So our goal is to learn the presence of chaos mathematically. Now first thing we will do here, that we will take a graphical approach to prove. We will graphical approach to prove mathematical theorems, and this we will do, and we will only restrict ourselves to a certain class of graph. which is like that. So this is called unimodal graph. So between 0 to 1, if a graph look like this, that it has only one maximum, it has only one maximum. So between 0 to 1, it is called unimodal graph. Graph. So from this unimodal graph, we will see the every concept of the chaos will prove actually mathematically, and to prove mathematically, we'll prove it in graphical sense by the use of property of this unimodal graph, and we will also prove that what properties these hold, and that's it. And okay, this is the thing. And then we will touch upon the subject of the fractals. So you see, I have told you that when the Lorentz was interested in to forecast a chaos, to forecast the weather, he found that the forecast, he can't give the exact forecast, but this forecast is in some confined space, in limited space. So every time he start from an initial condition, its future remains inside that. Suppose these regions is, if you see this kind of region, so if you say, if you start from any initial condition, it initial condition will be anywhere in this region. So this is called the strange attractor, because it's attract all the initial condition here, and it has very interesting properties, and it is called strange attractor. And it is basically, you will see that it's actually, if you mathematize this strange attractor, it will become like fractals. So we'll touch upon the things on fractals, and if time permits, I will also introduce a little bit of Hamiltonian chaos. That is basically a physics thing. That's it. Now, to means what we have to know a priori for this class. So that's basically, as I say in my thing, that only need 12 mathematical background. That means we need a little bit of that limit. We have to know the definition of the limit. Definition of limits, and we have to know definition of the limit, and a little bit of set theory. Not very hardcore set theory, but a little bit of set theory. These two we need, and that's these two things is very crucial for this course, because to tell the to prove the mathematical theorem, we need these two things. Obviously, we will see pictorially how we can prove that pictorially, but if we know these two things, it will be very helpful for us, so to prove the thing. And what we will do first, I will show you that in the course, I will show you first. We will touch upon what the predictability means, what prediction means, and how the definition of the prediction changed over the year. And second thing, I will show that how you can make a nonlinear model from simple that what Robert May used to, what Robert May in which way Robert May studied the population. So I will introduce that thing, and we will introduce how simple from the simple population equation made how simple population equation, and from by using this population equation, we'll see that this population equation in discrete population equation has the property of unimodal graph, and using that graph we will delve into the details of the chaos, then how to build the model, then we will see okay, I will see that if I have a map, and what is the stability means, what stability means, and how can we prove the stability of a dynamics or the map. And then what does periodic orbit means? What does periodic orbit means? And obviously stability means asymptotic stability, and asymptotic stability is nothing but at time t, when t become very large, where the system will go, means in which region the system will go, that is called the asymptotic stability. Means at time goes on, it will reach that thing in mathematical terms at t equal to infinity, where the system will go. Then I will show you the bifurcation. Bifurcation means when the stability of a system changes, some point where, means it's obviously depend on the parameter of that equation. So when I will change that parameter, some fate will change, means some fate of the system will change, and the new fate will emerge because of the parameter. So this is called bifurcation. It bifurcate because of change of parameter. And then from that bifurcation will show that how chaos bifurcation will show that from the bifurcation will show that how the sensitive dependence came in this simple unimodal equation. Then we will prove that if we have this unimodal thing, then we can prove that other two things, that transitivity and dense periodic orbit. Actually, this definition is I actually following the definition of whose name is, I think, Robert Divine. I am following these definitions because of Robert Divine, and we will follow this definition. So if these three things happens, we will say it chaos, and then we will see some interesting thing that that if you know little bit about universality means nothing but, as we physics people love to think in this way, that if I see something, and that means if I see suppose that if I see chaos here, it should have, means it not should have, if it have some universal property, that means whether the system is chaotic or not, or whether the map is, only by looking at the map it is means does not matter if the map is looking like this or this, if it has the unimodal property, means if it has only one maximum in this range, if it belongs to this class, can we say something about the system? If I can say something about the system, we can say that it belongs to the university class of the unimodal graph. It does not depend on the, it is sine, it means if you sine curve, if you see the sine curve also like this, and if you in the in some range, so 0 to, I think 0 to pi, this is pi by 2, I think pi by 2, and for the cos also you can make this graph. So it doesn't matter what actual function it is sine, cosine, or it is like that x into 1 minus x also follows this curve. So this curve, so it doesn't matter whether it is sine, if function is sine, cos, or x into 1 minus x, as long as it is unimodal. Can we say something about the system? And if I can say something about the system, we can say that these properties belongs to the universality, and universality class means that universality means whatever unimodal map it is, it will hold that things. So that's why we are interested in the universality. So we will see that universality. So we'll see that there is a beautiful things universality, and from this universality we can see that there is a close relation between the chaos and the second order phase transition. So those things. So I will not delve deeper into those things, but I will show you that they belong, there is a university class where these belongs. And then I will show you that strange means fractals and strange attractors. So these things will be the things that we'll mostly see in the class. So that's it. So in the next class, I will show you how the definition of the predictability, how change over the year, and how we can form equation. So in the next class, I will see the definition of the prediction, how it change over the year, and second thing is how we can model a population size as times goes on, how we can make a model out of a population size. And then we will see that what differential equation means in terms of population size, prediction of population size, and what means of difference. One is differential equation, one is difference equation. So that's all for the today's class. So if you have any question regarding the course, you can ask me now. Huh. Oh, it is basically if you attractor means if it attracts all the initial conditions. If you know something about the fixed point, means stable fixed point. Stable fixed point means all the initial condition who is in the neighborhood of that point. Suppose if you have a point here, and suppose there is a initial conditions, all initial condition, no matter what, its final future will be this. So this means these attract all the initial condition who resides neighborhood of this point. So that's why this point is called attractor. Now for the case of Lorentz attractor, the Lorentz attractor is not a single point. It is basically a surface, and that surface is characterized by fractals. So suppose like this kind of surface. Now this, if you start from any initial condition, means it will attract all the initial conditions wherever you start. It doesn't depend, but it will at last it will settle down on this surface. So that's why this surface is called the strange attractor, means it attracts all the initial condition that resides neighbor in the neighbor of that attractor. So that's why it's called attractor. Okay, so then let's see you in the next class. It is in the Friday. We will show some equation there. Okay.